All right, ladies and gentlemen. So we're going to do a couple things today. We're going to go over some formatives. The first one is going to be our formative from way back towards the beginning of the unit with vector formative. So I'm just going to go through the answer keys. I'm not going to show you all of, we're not going to go through the steps on everything together, just because I feel like that might take too much time if we go through all three like that. But if you have questions about anything, please do ask. Otherwise, I'm just going to keep going through because we have three formatives to get through today. So the first one being that vector formative. So if we're looking at that vector formative, the first thing we got to remember is that we're doing addition of vectors. So we got to find our vector components. You guys did a really good job finding the vector components. I'll show you my work down here where we have our different angles, finding our X and our Y components for those different angles. The big thing that I saw issues with was the positives and negatives. You guys did a really good job of figuring out which one was sine and which one was cosine for each of your four different vectors. But the positives and negatives based on the different quadrants was a big part that was missing, which is why the resultant vector might not have come out correctly. So especially like the X is negative for quadrant 2. The X and Y are both negative in quadrant 3. In quadrant 4, just the Y is negative. So figuring out those different components to the X and the Y, whether or not they're positive or negative, was our big mistake. But if you're looking, you should have gotten these values. And when we added our X components together, we should have gotten 10.1 newtons for our total resultant vector in the X direction. In the Y direction, when we added our four vectors together, we should have gotten 10.1 newtons in the Y direction. Once we got both of those vectors going in both directions, we should be able to then calculate our resultant vector with its magnitude and direction. You should have found out that the magnitude was 14 newtons and it was going at 45 degrees because it was in the first quadrant. Are there any questions on this formative or the vector formative? All right, so then we're going to go to a little bit more recent of a formative, which was our Newton's laws formative. So the first question for Newton's laws was talking about the three laws of motion that Isaac Newton came up with. So each one, A, B, and C, was one of Newton's three laws. 1A was Newton's first law, stating that a body in motion will stay in motion with the same velocity unless acted upon by an external force. This one, or this whole section, you guys did a pretty good job on. The big thing was that when it says same velocity, that red section right here, a lot of people were saying speed, and I did count that as an error just because speed only gives us a magnitude or a value. That velocity tells us which direction you're also going in. So make sure that you're keeping velocity because it's telling us speed and direction. So we want that magnitude and direction involved with the body staying in motion. For part B, which was Newton's second law, we have the acceleration of an object is proportional to the sum of the forces on an object and inversely proportional to the mass of that object. The big thing there is if we wrote this out in equation form, we have the sum or the acceleration equals the sum of our forces times the inversely proportional to the mass or divided by the mass. So I did see a few people switching acceleration and force, and we can't do that just because mass is force is divided by mass, which means that if we switched acceleration and mass, we would have the sum of our forces equals acceleration over mass, which is not something we want. It is acceptable if you did change these two, it would have been acceptable, but not the force and acceleration. And then the last one, Newton's third law, for every force, there's an equal and opposite force. So if object A applies 10 newtons of force to object B, then object B must also apply a force of 10 newtons to object A. So those were Newton's 3 laws. They were actually verbatim from the homework that you guys did with Newton's laws. Are there any questions on any of Newton's 3 laws? All right, so then part 2 or question 2 talked about the purple playground rhinoceros and little Susie arguing about their Matchbox cars coming to a stop. The rhinoceros said that the natural tendency for all objects is to be at rest unless a force is applied to them. This is why he pushes the cars and they go, and when he pushes them harder, they go faster. Little Susie argues that the wheels pushing against the ground cause the car to stop because there's a transfer of all the car's force onto the ground, so it comes to a stop. So what the purple playground rhinoceros said that was correct was that when he said when he pushes on the cars, they go, and when he pushes on them harder, they go faster. And this is because of Newton's second law. So if we think about that, he's applying more force, which means if the mass of that car didn't change, if he applies more force, there has to be a larger acceleration, or that car is going to move faster. So that was correct. But the incorrect part was his first statement that said that the natural tendency for all objects is to be at rest, which we just wrote all the way up above in question 1A, that a body in motion is going to stay in motion with that same velocity unless acted upon by an external force. So objects that are moving want to stay moving. So this is incorrect because this opposes all of Newton's first law, because the object's going to stay in motion with that same velocity unless acted upon them by the external force. So it's not all objects are going to be at rest, because when an object is in motion, it wants to stay in motion. So this is incorrect because it says all the objects are always to be at rest, and that is not the case. Any questions on the purple playground rhinoceros and his correct versus incorrect statements? All right, then we have little Susie, and little Susie, what she said that was correct was that the wheels apply a force onto the ground. If they don't, it wouldn't turn. So they're applying that force to make the car move. What she said that was incorrect was that the force is going to transfer all the forces from the car's wheels to the ground, and that's not the case, because force does not get transferred to other objects. There's going to be an external force that is opposite of that car, which is why the car slows down and comes to that stop. So that frictional force is opposing the applied force, which is why it comes to a stop instead of transferring the force. And then if you were trying to correct them, you would tell them that the car would continue rolling with that same velocity if there's no opposing forces. However, we know that the car is going to slow down and come to a stop because there's that force of friction resisting the movement of the car, or opposite that applied force. Are there any questions on this section or about this formative? All right, we have one more force. Our final, our one more formative, the wrong thing. Our final formative, what we did on Thursday. So the first thing I do want to talk about is this free body diagram. You guys did a great job coming up with that. There was air resistance and there was gravity because the object is falling, or the purple playground rhinoceros is falling, and he has a parachute. So there's air resistance pulling him back up, or trying to pull him back up. The issue was that a lot of us were trying to find that acceleration of just the air resistance. So we set this equal to mass times acceleration to find acceleration, but it does ask for the acceleration of the purple playground rhinoceros, not just this force up here, but the sum of our forces, or the total force. So we needed to find our force of gravity, or our weight, which we get to be 23,000 newtons. We're going to find that sum of the forces, and we'll figure out that the purple playground rhinoceros is falling with a force of 5,000 newtons towards the ground. So we can then solve for our acceleration and find our acceleration to be 2.2 meters per second squared going towards the ground. Any questions on number 1? All right, the second one, couple things that we're missing were this right here. This free body diagram, make sure you are drawing one so you know what forces are exerted by the object or the person. The next thing that I saw was an issue was that there was this wonderful applied force that people were drawing. And yes, there would have been an applied force if she didn't take her foot off the gas, which means there's no applied force anymore. She's not pushing that car forward anymore. It's just decelerating or slowing down. There's no more applied force, just that frictional force. The last thing, what does this deceleration mean? What does that tell us?
Negative value.
Exactly, negative value right here. So our acceleration should be a negative or should be slowing down, or it's the opposite direction of our motion. So make sure you are including a direction in this problem. Are there any questions on anything we've gone over today or on this formative specifically?
Can you went over question 1 again?
Question 1. Yeah. So it says a 2,300 kilogram purple rhinoceros parachutes from the passing plane onto a playground. When deployed, the parachute provides 18,000 newtons of air resistance. Draw the free body diagram and calculate the acceleration of the purple playground rhinoceros. So we draw that free body diagram telling us that we have gravity pulling us down and our air resistance trying to oppose gravity. And it told us that the air resistance was 18,000 newtons. And we know that this has 2,300 kilograms for the purple playground rhinoceros. So it tells us we want to find the acceleration going down. So we want to find our acceleration, which means we have to find the sum of our forces to figure out which way he's accelerating. So when we add our forces together, these are only in the y direction. So we're going to sum up our forces in the y direction. And we have air resistance going up and gravity going down. You can choose which direction you want to be counting as positive and negative. I'm going to say that my going up is positive, so air resistance minus my force of gravity, saying that my gravity is a negative value or going down. I have my air resistance and I need to find my force of gravity so that way I can figure out what my total force is in the y direction or in order to figure out my acceleration at the end. So in order to figure out my force of gravity, I need to know my mass and my acceleration due to gravity on Earth, which means that if I know the mass to be 2,300 kilograms, and we know the acceleration due to gravity is 9.81 meters per second squared, I can figure out my force of gravity, which ends up being 23,000 newtons when rounded. Are you okay with that part so far?
Yeah.
Right. So then I just plug in my two values. So I have my sum of my forces in the y direction equals my 18,000 newtons minus my 23,000 newtons to get a negative 5,000 newtons. And I know that the sum of my forces in the y direction equals my mass times my acceleration, because the sum of your forces always equals mass times acceleration of the entire object or person, which means I can plug in my values. So negative 5,000 equals my 2300 times my acceleration, which means I can find my acceleration to be that negative 2.2 meters per second squared, or 2.2 meters per second towards the ground. Are you okay with that?
Can you do force gravity minus force air resistance?
You can, and that just changes your positive or your negative to a positive right here and right here and right here, which just means that you are choosing this to be your positive and this to be negative.
Okay.
You're just changing which way your direction is, that you're choosing to be positive versus what you're choosing to be negative. And that's fine as long as your work shows that the entire time. Any other questions?